Good morning. The purpose of this little recording is to help you with Section 3.6, the Mathematics of Finance. What I'd like you to do to start out is to open your books to that section. You'll find many good examples there, and you should read through those thoroughly on your own. Now, if we take a look at this section, what you're going to see is there's going to be several formulas for working with money. Obviously, that's a favorite topic. Some of these you may have seen when you were younger. Some will be brand new today. The first formula we're going to look at is the one for interest, which is compounded annually. When we say annually, we mean every year. If we take a look at this formula, what it says, to calculate interest, the amount at the end, what you can do is take the principal times 1 plus r to the n. What I would like you to take note of is that this formula is basically our formula for exponential growth. We've had it with population. We've also just had it in this form. Remember, in this form, if b was greater than 1, we had growth. If it was between 0 and 1, we had decay. Now, if we look at this formula modified slightly, what we'll have is the interest formula when it's compounded more than once a year. What that means is you are actually going to be getting interest on your interest at several different times during the year. If you look at this formula, what you'll notice is that the formula has to be modified. What we need is we need to take a look at the number of times a year that we're compounding. And we put that into the formula right here and right here. Let me give you an example of how that works. Suppose Paul invests $400 at 8% annual interest compounded monthly. Let's find the value of an investment after 5 years. Well, if we take a look at this problem, you'll notice that that's the formula we're going to use. A is equal to P times 1 plus R over K raised to the KT power. P would be 400. R is 0.08. That's our rate. K is 12. That's compounded monthly 12 times a year. And our T would be 5. Now watch how this gets substituted into the formula. What they're going to do is put in the 400 for P right out here. They're going to put in the rate, 0.08, but divide it by 12. And up here you have the 12 times 5, K times T. Notice that you could just as easily write as 60. So basically what you're going to do when you enter this into your calculator is start in here. Take the 0.08 divided by 12, add 1. Take it times 400. First, raise it to the 60th power, and then take it times 400. And what you should end up with is 595, about 94 cents. Why don't you try that and make sure that you've got that down? So again, if we take a look at this formula, what you'll see is that the compound interest value of an investment can be given by A is equal to P times 1 plus R to the K raised to the KT power. Now, again, if you look at that, the way we calculate it is we take the R divided by K, add 1, raise it to this power, and then multiply by P. Now, I do want to tell you that there's another compounding formula that comes into play. It's compounding continuously. This happens many times in science class. For example, if you have bacteria in a petri dish, you can't tell them to compound only 4 times a year. They're compounding continuously. In which case, then we need to use this formula. Some of you might have learned it last year as PERT. It's A is equal to P times E to the RT. And if we take a look at an example of that, what you'll notice is that we could do the same problem, but have it compounded continuously. Suppose Paul invests his $400 at 8% annual interest compounded continuously. Find the value of his investment in 4 years. Well, now as we take a look at that once again, you'll notice that our principal is the $400. The rate is 0.08 and the T is 5. When we substitute that in, you'll notice we have to use the number e. So what I would do in putting in your calculator, and you can try this with me, is you can find the e to the x button and take e, put parentheses around the 0.08 times 5, and then take that times 400. Now again, you'll notice you get a slightly higher rate. It's not hugely different, but it is a slightly higher amount at the end because you're compounding continuously. Now, what we're going to do next is we're going to jump up to a formula that you probably have not seen. So what I would like you to do is open to page 311 in your book. Open up to page 311. This formula is what we call the future value of an annuity. An annuity is simply a series of fixed payments. For example, maybe I would have a savings plan where every month I put in $50. Now what happens is that each month I get interest. So the money I put in first actually gains more interest over the time than the money that I put in at the end. Think about that for a second. It should make sense. Now, the future value of an annuity, consisting of n equal periodic payments of r dollars at an interest rate of I compounding period interval, is given by this. The future value is equal to r times the quantity, 1 plus I to the n minus 1 over I. What you're going to find if you look at your book, these will be problems like 47, 48, 49. Let's just try one together to make sure that you can do it. Let's take a look at question number 47. On 47, you're going to notice, as you read through it, it's going to ask you about the future value of an annuity. And in this case, as we read through it together, the first thing I want you to notice is that it says there's a 7.26% interest rate. What we have to do for our I is not use the 7.26%. Instead, what we want to do is we want to take that 0.0726 divided by 12. And that's because we're making monthly payments in this problem. That means that our monthly interest rate is about 0.00605. Notice how many places I carried that out. The R is $50 because it says we're going to put $50 into an account every month, which means then that my number of payments over 25 years is going to be 25 times 12, or 300. When we put that into our formula, you'll see that we'll have 50 times 1.0065 raised to the 300th power minus 1, all divided by 0.00605. Now, what I would suggest is that you do that part in parentheses first. Try it. Take 1.00605 raised to the 300th power minus 1 and divide by 0.00605. Last, take that answer, 844.229, and take it times 50. This gives us the future value of an annuity. So in other words, if I take my $50, deposited every month for 25 years, and I'm earning 7.26% interest, at the end, I'll have this much money. Another formula that we'd like to take a look at is what we call the present value of an annuity. What that means is something like this. Let's suppose I want to buy a house. When you buy a house, most of us don't have the money to pay cash. So what we need to do is we need to take out a mortgage. That means we promise to pay a certain amount each month to pay off the house. Now, obviously, there's going to be interest involved. If we take a look at this formula, what you'll notice is that the PV stands for the present value. So in our example there, what that would be is the price of the house, the amount that you want to borrow. The R would be your monthly payment. The I, again, is the interest rate per month. And the N would be the number of payments. Let's look at an example of this. Take a look in your book at question number 53. On 53, what you should see is that you've got a problem about a mortgage payment. In there, the present value of your house is $86,000. It says that you are going to pay 8.75% interest. And you're going to do this for 30 years. Now, as far as the workings of our formula, you'll notice that my I is not 0.0875. Instead, what I have to do is take that 0.0875 and divide it by 12, because we're going to make monthly payments. Now again, notice I carry this out many places. In fact, you might want to just carry that out and leave that in your calculator to use later. Our present value of the home is $86,000. That's what we're going to borrow. And our number of payments, if it's 30 years, would be 360 payments. Now watch how this gets substituted into the formula. In this case, what we'll do is, since we know the present value, we'll put that on the left-hand side. There's the $86,000. That's your present value. We don't know the monthly payment, but we can fill in the rest. And in the formula, what we'd put then is 1 minus 1.00722917 raised to the negative 360th power, all divided by that 0.00722917. Again, I'd start inside the parentheses and calculate this. So take 1 minus this raised to the negative 360th power, press equals, and divide by this. You should get 127.1127 approximately. Again, I carried that out quite a bit. Simple algebra tells us we divide, and this figure over here ends up being our monthly payment. Monthly payment. Now, if you want to know how much the house actually costs you if you pay it off over 30 years, take this number times 30, and then take it times 12. Monthly payments for 30 years. Or you could just multiply it all by 360. What you'll see is that it's considerably higher than the $86,000 that you borrowed. These are the formulas that you're going to be working with on lesson 3.6. Now, just a couple of reminders that for Mr. Hilding's classes on Wednesday, you should be working out of section 3.6, numbers 2 through 40 even. Thursday, you're going to finish up section 3.6, and on Friday, this is a little messy, but on Friday, we're going to have a quiz on 3.1 to 3.5. Now, you are going to have time to work here in class. Please use that time productively. If you're mixed up on things, either ask the substitute to replay this video or look at the examples in the book and consult a friend. I think you'll be able to get through it, and when I get back, I can help you with these problems some more. All right. Have a good day.